When upgrading an electrical service from 1200 amps to 2000 amps, several factors must be considered to ensure a safe and compliant installation. A key decision involves whether to utilize existing 350 NCM conductors by adding more conduits or to replace them with larger 500 NCM conductors. Let's explore an alternative route which involves adding conduits for more 350 NCM conductors. This approach offers several advantages. Firstly, it utilizes the existing 350 NCM conductors, which in this scenario are relatively new and have demonstrated reliability. Secondly, it may prove more cost-effective than investing in 500 NCM conductors, particularly if extensive conduit runs are involved. However, there are also considerations to keep in mind. Firstly, installing additional conduits will inevitably increase labor and material expenses. Secondly, expanding the existing panel board or switchgear might be necessary to accommodate the increased number of conductors. Thirdly, ensuring that the selected conduit size and fill rates adhere to code requirements for the number and size of conductors is essential. To determine the number of additional conduits required, a calculation must be performed. Begin with determining the current rating per conductor. Then determine the total current required, which is 2000 amps in this case. The calculation is as follows: number of conduits required equals total current required divided by current rating per conductor times number of conductors per conduit. Assuming 3 conductors per conduit, the number of additional conduits required is 2000 amps divided by 350 amps times 3, which equals approximately 1.905 conduits. Therefore, you would likely need to add 2 additional 4-inch conduits to the existing 4 conduits. Consider the following additional points. Code compliance is paramount. Ensure the upgraded installation adheres to all pertinent electrical codes and safety regulations. Cable support is vital. Provide adequate support for the conductors within the conduits to prevent damage and maintain proper insulation spacing. Heat dissipation should be considered. Evaluate the heat dissipation characteristics of the conductors and implement sufficient ventilation or cooling measures if necessary. Grounding is critical. Maintain proper grounding throughout the upgraded system. Let's look at some of the NEC tables that will help you with determining the size of the unrounded and neutral conductors. The primary sections that cover conductor ampacity are Article 310 and its associated tables. When dealing with conductors and conduit, you'll often reference Table 310.16 for ampacities of insulated conductors rated up to 600 volts, not more than 3 conductors in a raceway or cable or earth, based on ambient temperature of 30 degrees Celsius, 86 degrees Fahrenheit. For 350 MCM copper conductors with a 75 degrees Celsius insulation rating, the ampacity is typically 310 amps. However, in this case, the question mentions using 350 ampacity for the 350 MCM conductors. It is likely that the 90-degree column is being utilized, as it is a common industry practice to use the 90-degree column for ampacity adjustment and correction factors, then direct to the 75-degree column when determining the final allowable ampacity. Table 310.15. 8.2 addresses adjustment factors for more than 3 current carrying conductors in a raceway or cable. If you have more than 3 current carrying conductors in a single conduit, you need to apply adjustment factors to reduce the allowable ampacity. The specific adjustment factor depends on the number of conductors. For example, if there are 4 to 6 current carrying conductors, you'd apply an adjustment factor of 80%. If there are 7 to 9 current carrying conductors, the adjustment factor is 70%. Table 310.15. 3. I provide correction factors for ambient temperature. If the ambient temperature is higher than the temperature listed in Table 310.16, you need to apply correction factors to reduce the allowable ampacity. The specific correction factor depends on the conductor's insulation type and the ambient temperature. For example, if you are using a conductor with a 75 degrees Celsius insulation and the ambient temperature is 40 degrees Celsius, you would use the correction factor associated with that temperature. Ensuring proper conduit fill is crucial for heat dissipation and ease of installation. Chapter 9, Table 1 provides the maximum percentage of raceway in cable fill. For more than 2 conductors, the maximum fill percentage is 40%. Annex C provides examples of conduit fill calculations using different types and sizes of conductors. It's essential to calculate the total cross-sectional area of all conductors in the conduit and ensure it doesn't exceed 40% of the conduit's internal area. Selecting the right conduit size is critical to accommodate the conductors and allow for future expansion if needed. Table 4 in Chapter 9 lists the dimensions and percentage area of raceways for conductors. This table helps you determine the internal area of different conduit sizes, which you'll use to calculate the allowable conductor fill. Remember, the NEC specifies requirements for conductor support to prevent strain on terminations and ensure proper insulation. Article 314.17 covers conductor support requirements in boxes and conduit bodies. Conductors must be supported within a certain distance from the enclosure, depending on the conductor size and the type of enclosure. In addition to ampacity, voltage drop is an important consideration when sizing conductors. Excessive voltage drop can lead to equipment malfunction and reduced efficiency. Section 210.19 A1. Informational Note Number 4 and Section 215.2 A3. Informational Note Number 2 provides guidelines for voltage drop. Generally, it's recommended to limit voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, you'll need to know the conductor length, current, and impedance. Online voltage drop calculators can simplify this process. Grounding and bonding are essential for safety and to provide a low impedance path for fault current. Article 250 covers grounding and bonding requirements. Ensure that the grounding electrode system is properly installed and connected to the service equipment. Bond all metallic components of the electrical system, including conduits, enclosures, and equipment frames. Size the grounding and bonding conductors according to NEC tables. Surge protection devices, SPDs, can help protect sensitive electronic equipment from voltage surges caused by lightning or other transient events. Article 285 covers surge protection requirements. Consider installing an SPD at the service entrance and the downstream panels to provide comprehensive surge protection. Heat dissipation is a critical factor in conductor sizing and insulation. Overheating can damage conductors and insulation, leading to equipment failure or fire hazards. Ensure that conductors are properly spaced and ventilated to allow for heat dissipation. Avoid bundling conductors tightly together as this can trap heat. If necessary, use larger conductors or forced air cooling to manage heat. Short circuit current rating (SCCR) refers to the maximum fault current that a component or system can safely withstand. It's essential to ensure that all electrical equipment has an adequate SCCR to prevent damage or failure during a short circuit event. Article 110.10 addresses SCCR requirements. Coordination studies can help determine the available fault current at different points in the electrical system and ensure that equipment is properly protected. Always consult with a qualified electrical engineer to perform the necessary calculations and ensure that the upgraded electrical service meets all applicable codes and standards. Remember that this information is for general guidance only, and it is not a substitute for professional engineering advice.